All right, life is good. Okay. Okay, for real this time. So we've got our curve given to us. They actually give us our derivative, so we know what dy dx is. We don't have to find it. Show that the curve does not have any horizontal tangent lines. So there's kind of a couple different ways that this could go. Actually, no, there isn't, because we know dy dx. What would have to happen for this curve to have a horizontal tangent line? Exactly, right? The numerator would have to be equal to 0. If this question was vertical tangent lines, we would say the same thing, but we would work with the denominator. So horizontal tangent line in this case means that the numerator equals 0. Can the numerator equal 0? Yeah, right? So dy dx equals 0 if y equals 2. So I'm kind of stating something that I know, and that's just something you can kind of do by inspection, right? So let's then use that. Let's put 2 into our original curve. And what's going to happen is we'll just find, and this is how like an implicit function can go, it may be possible that whatever that curve does on the graph, it just completely avoids the vertical line x equals 2. So it never crosses over x equals 2. And since they're telling me that it, I mean, they are in here telling me that I don't have any vertical tangent lines. Good morning. Or any horizontal tangent lines. You know, I'm assuming that is what they're telling me. They're telling me there are no horizontal tangent lines. So we end up with 6x minus 3xy. So I'm going to write minus 6x. This is a really easy one. Plus y cubed. So that's going to be 8 equals 40. Yes. Right. So then you end up with 8 equals 40. And that's enough to tell you that there are no solutions, there are no points on this curve where y equals 2.
Wait, where do we get squished?
The beginning. Consider the curve 6x minus 3xy plus y cubed. And I plugged into 6x, another negative 6x, and then 8 for 2 cubed. Yep. There are no points on the curve with a y value of 2. This isn't standard, anything that I'm writing. I'm just kind of coming with this off the top of my head, but I think it's going to be pretty good. There are no points on the curve with a y value of 2, since 8 does not equal 40. Last time I checked. So something has to, I mean, that's kind of what has to happen. You need to get something, if there are no horizontal tangent lines, but you clearly can make the the numerator 2, then something's got to go wrong when you make the denominator 2 in the original equation. If we jump over to Desmos real quick. It was 6x minus 3xy plus x cubed equals 40. Yeah. Ooh. Y cubed. Okay, I was going to say, is my sentence wrong? Yeah. And we wanted x to equal 2? Y to equal 2, right? Yes. Y equal 2. I was going to say x could equal 2, right? Y equals 2. So as you can see, if I graph the line y equals 2, it is actually an asymptote, a horizontal asymptote of those graphs. So the curve does approach y equals 2 from both sides, but never actually gets there. So they found a curve that did that and set the problem up that way. So that would happen.
You know, I understand what we just did, but there's not a connection I would have made in like
Oh, yeah, no. Well, how much have you done with implicit functions as well, too? It's weird. Like we always think of, like a lot of the stuff that we just normally think about kind of goes out the window with implicit relationships. And now think about this. What if I made this, what if the original equation was 8? That actually ends up being really weird because you end up with actually a horizontal line. It always works, so that's interesting. I thought something different was going to happen there. You'd end up with 8 equals 8, which would mean all solutions, so all x's would work, and you end up with that's kind of weird. I thought I was actually just going to get I actually thought I was going to get a horizontal tangent line there, but I didn't, so Okay, that's all we needed to know for that problem. Letter B says, show that the curve has a vertical tangent line when y equals -2. So sort of the same deal. This time, though, we have a vertical tangent line when dy dx is undefined, and dy dx is undefined when y squared minus x is 0. Or y squared equals x. So we'll just look to see if there's any easy way to plug that in. If like I had a y squared, I might go for the simplification. Like if there was just y squareds in here, I'd be like, oh, great. You know, I'll just put x's in there. But I do think I need to change all my x's to y squareds. I'm curious as to what's going to come out here. Let's see. So we end up with 6y squared minus 3 x y, 3y cubed. What am I doing? I'm plugging in x for y squared for x. So 6y squared. I'm thinking ahead and I don't know. Okay. Yep. Minus 3y cubed plus, I feel like I'm doing, yeah. Plus y cubed equals 40. Yep. I actually don't think I'm doing what I want. This is not what I want to do. This would be what I would do if I needed to solve for the y value. But I don't need to solve for the y value because they gave it to me. Sorry. So yeah, we should plug that -2 in. I'm thinking here I'm going to end up with a cubic equation, an equation with a third power in it that I don't know how to solve, but then it's hitting me that it doesn't matter that I don't know how to solve it because they already solved it for me. So this is what you have to do when they want you to find a vertical tangent line without a given x value. But I know my x value. So y squared equals x. Let's plug into that instead and make our lives easier. What does x equal? Yeah. X equals 4. Yep. Okay, so our point is 4 comma -2. And now all we have to do is verify that 4 -2 is on the curve. Okay, because it's great. Plugging 4 and -2 into this will give you a non-zero over 0 because you'll end up with 4 minus 4 in the numerator or the denominator. But the question is that point even on the line? Because if it's not, then that's great, but it's not going to. You're not going to have a vertical tangent line there because that point isn't on the line. So then, just like yesterday, we'll verify that 4 -2 is on the line. And that's just plugging both of those in. So now we have 6 times x, so 6 times 4. I'll do both steps for you here. 3xy, so that's going to be 3 times 4 times -2, plus y cubed, that's -2 but cubed. And that should equal 40. So we end up with 24 plus another 24 minus 8. So we do. So that tells us that that point is on the line. Because that's what, or the curve, I should say. And that's what it means to be on the curve. Any point on the curve, when you plug its x, y's in, should make the equation true. Any point that's not on the curve should make it false. And then, yeah. I'm gonna write a follow-up sentence down here now that I don't need to look at my. So I'm gonna say, show that there's a vertical tangent line. There is a vertical tangent line. At 4 -2, now that I have the whole point. And the two things that I figured out were that that point is actually on the curve and dy dx is undefined. So those are the two things I'm going to write in my explanation. This point is on the curve. And dy dx is undefined. Yep. So yeah, so I think the thing that you can easily miss in this problem, especially not later on because we're just talked about it, but fast forward 2 months, we're doing integrals and all kinds of other things. You do this problem and you get here and you just say, oh, x equals 4. This is easy. If I put 4 negative 2 into that dy dx, I get undefined. But that's not enough. You also have to check to make sure that the point's actually on the line. Because you could do this with any other y value and you would get an x here, but then that point's not on the line, most likely, unless there might be another one, but just some random one most likely would not be on the line. Sound good? Or I keep saying line, but of course I mean curve. Okay, last thing I want to talk about, I want to take a look at number 10 for a minute, just to kind of get you guys a head start. I'm actually going to stop recording and re-record just so I can get a second video out of this for future use. We'll stop there.